How can evolution and learning best be combined? When optimizing for fitness, is it better to learn and evolve in concert, or should one approach be favored? And how do the answers to these questions depend on the environment and the exact types of learning in question? Today, I'm going to discuss some of our recent work on answering these questions in tunably rugged NK landscapes. The combination of learning and evolution has long been of interest to biologists and cognitive scientists, stretching back to the time of Baldwin. Recently, however, advances in artificial intelligence have made studying the interaction between learning and evolution an item of algorithmic interest as well. Motivated by both of these disciplines, we sought to answer four basic questions. First, given a fixed budget of optimization events, is there an optimal trade-off between how much time a population dedicates to lifetime learning versus evolutionary learning? Now, what do we mean by budget exactly? In biological terms, this budget might relate to an agent's lifespan. A longer lifespan allows for more learning, while a shorter one could allow for faster evolutionary adjustments to a changing environment. Second, how does the trade-off change as a function of the difficulty of the fitness landscape? Third, how does the trade-off change as a function of the type of individual learning? In our case, we examine the difference between what we call optimal individual learning and stochastic individual learning. And fourth, how does the trade-off change as a function of the type of evolutionary learning? We distinguish primarily between Darwinian or standard evolution and Lamarckian evolution. To study these questions, we use the NK model first introduced by Stuart Kauffman in 1987. I'll assume that most of you are broadly familiar with NK models and won't bore you with the details. The important thing to note is that NK landscapes are tunably rugged. By changing the parameter k, we can easily alter how challenging it is to optimize fitness on the landscape. Our basic approach is as follows. First, we initialize a population of agents, which each consist of a binary genotype of length n. Using the landscape, we can easily assign a fitness to each possible genotype. Each agent is capable of doing individual learning, which consists of examining its local fitness environment and making a single change to its genotype. The population as a whole can also perform evolutionary learning, which consists of the classic steps of selection, reproduction, and mutation. How do we interface these two systems? It depends on the type of evolution. For both Darwinian and Lamarckian evolution, the fitness of an agent is calculated based on the genotype that results after lifetime learning is complete. For Darwinian evolution, however, it is the original genotype that is passed on to the next generation. For Lamarckian evolution, the changes accrued by lifetime learning are passed on directly. I alluded earlier to the concept of a budget of learning events. For all of our experiments, we wanted to keep the total amount of learning in the population constant, even as we varied the balance between lifetime and evolutionary learning. To accomplish this, we tested 7 different schedules of learning events with a different number of lifetime and evolutionary learning events, or rather a different number of lifetime learning events preceding each evolutionary event. This allowed for a more fair comparison between each of the different experimental conditions. Finally, I just want to briefly explain the differences between optimal or steepest descent lifetime learning and stochastic lifetime learning. For steepest descent lifetime learning, each agent checks every adjacent position in the parameter space and takes the best step. In stochastic lifetime learning, an agent checks only one random adjacent position and moves there only if doing so is an improvement. All right, so with that out of the way, we can finally analyze the results. First, we're showing a couple of fitness trajectories for different ratios of lifetime and evolutionary learning using steepest descent and Darwinian evolution. It's clear that each of these strategies is capable of improving performance over time. What's most interesting is that in the hybrid case, even when performance dips as a result of lifetime learning not being inherited, performance very quickly recovers to near optimal levels. Indeed, this trend is borne out even further when we take a look at the overall best performance across task difficulty. We see a very clear inverted U-shaped curve in which hybrid strategies outperform either extreme, with the difference only getting more pronounced as task difficulty increases. This, I think, is the most noteworthy result from our research, and we were interested in seeing whether it would hold across variations in lifetime and evolutionary learning type. If we take a look at the results for Lamarckian inheritance, we see that there aren't any of the dips in performance like there were for the Darwinian case. This makes sense intuitively, as lifetime learning is passed on to the next generation. Despite this, we still see the exact same inverted U-shaped curve when we examine the results across task difficulty. And finally, we can see the results here for different types of individual learning. We noted that for Darwinian inheritance and stochastic lifetime learning, the inverted U-shape almost completely disappears, while it is still somewhat present for the Lamarckian inheritance case. Why might this be? One possible explanation is that the Darwinian inheritance provides an evolutionary pressure for agents to not only be in areas of a high fitness, but also areas of rapid possible ascent. That is, it is adaptive for an agent to be somewhere steep in the fitness landscape because it can take advantage of that steepness during lifetime learning. However, when agents use stochastic lifetime learning, it is much more challenging to take advantage of such areas of rapid ascent, since there's no guarantee the agent will even consider those changes. This could explain why hybrid strategies do not seem to offer any benefit in the Darwinian case. So to summarize, We sought to analyze the interaction between learning and evolution using a simple, tunably rugged landscapes, hill climbing, and genetic algorithms. We found that in a variety of settings, a combination of learning and evolution outperforms either in isolation, with the differences becoming stronger as task difficulty increases. Of course, there are still a lot of unanswered questions that would be worth investigating, such as the effect of more advanced learning algorithms and more complicated environments. Thank you for listening, though, and if you have any questions, please stop by our Zoom room. Thank you.